categories of G modules. Is that large enough? So this is joined with von Penkov, some of you may have wondered what was Alexei referring to the other day. In his talk, he was talking about some joint work of Penkov, Sarganova, and myself. That's very much the same philosophy as what I'm talking about today. But in fact, that work is geometrical, uses D models, whereas this work so far is purely algebraic. Pretty vague title. It's partly a send-up of an old paper by Bernstein, Gilfun, and Gilfun called On a Category of G Modules. I think it's one of the great titles in representation theory. Of course, that category is now called Category O. So I should say that classical category is O, which actually depends upon some choices. So you start with semi-simple Lie algebra, Borel subalgebra, and a Cartan subalgebra of the Borel subalgebra. And then you attach a class of objects to this data. And probably most of you know, but I'll just say very quickly, so that we're all on the same page, that you want your G modules to be finitely generated over the enveloping algebra. You want every vector to generate a finite dimensional B submodule. And you want H to act semi-simply. Now, of course, since H is a subalgebra of B, and B is acting locally finitely, H acts locally finitely. And so then asking that H acts semi-simply is the same as asking that H acts diagonalizably in the module. This is an awfully lucky guess on the part of BGB, because this category turned out to provide many people with employment for the last 40 years. And it's still a thriving industry. So I'm certainly going to try to build on what they did, but in the process I'm going to have to leave category all behind and work in a much larger category, about which less seems to be known. But I'll try to motivate the necessity of enlarging the category. All right, so I want to two more things on this whiteboard before I go to the green board. So then, another classical category well, I'll write it as MGK. And here, on K is the symmetric subalgebra. So again, G is semi-symmetric. And for now, what I'll mean by this category is G modules, which are locally finite with respect to K. I could impose further conditions, and I'll come back to that. Again, Gelfand and his school considered certain natural subcategories of MGK, and it was apparently important problem to describe these categories in terms of we now call the theory of quivers. Okay, but I won't dwell on quivers today. All right, so these categories, in fact, both get mentioned in Gelfand's talk to the Nice Congress in 1970. Who here participated in the Nice Congress? No? So,
72, I think.
sorry?
72.
I believe it was 70. We're having a lot of difficulty with our memory dates, so we'll discuss it. Yeah, so
You're right.
It should have been 70.
It was 70.
and probably the proceedings didn't come out until 70. So there's a famous paper by I and Gelfand. Nice, ICM. And I'm going to go out on a limb and assert that it was 1970. One interesting point is that, of course, in the tradition of the Cold War, Gelfand was not granted permission to show up and give the lecture himself. So the lecture was given by my then professor, Dan Mostow. All right, so the first basic question that you can ask is, well, two categories. I'm saying TWO. There's no pun on higher category theory. If two categories appear naturally in a context, there ought to be some way of relating one category to the other. In fact, this has been a very fruitful idea. You can go in both directions. You can try to start with an object in GK modules and go to an object in category O, or you can try to start with an object in category O and go to an object in GK modules. But of course, what does it mean to go to another object?
So for GK, do you make any semi-simplicity assumption?
Yeah, so of course, in order to say anything kx.
Sure.
So, let's take this to be the introduction. And I should start with the article. Sorry?
I think you should start with the board on the back.
Start with the word on the back.
That's what I would call it.
Okay.
Well, neither work really well.
Next time I'll bring my beamer. All right, so let's consider a diagram. So let's consider that I have a diamond about this. So the B and K are subalgebras of G, and as before, we'll take B Burrell subalgebra on K. And now I'm not going to restrict myself yet to the symmetric case. So take K to be a reductive of G subalgebra. I need to justify going to this greater generality, but I hope that quickly you'll see the point. And then T will be part-time subalgebra of K. Then I'm going to write CGT, going to be the category of GT levels that are semi-simple. Now let's keep in mind, so that I can make clear how my assumptions relate to the assumptions of other talks. Not assuming that K has the same rank as G. All I know is that the rank of K is less than or equal to the rank of G. So that my T is not necessarily a part-time subalgebra of G. So then, it's not quite clear how D should work into the discussion here. The first thing that one can do, even before a choice of B, is one can consider a functor, which I've been writing gamma kt, and it's the adjoint functor to the inclusion. Put in a more down-to-earth way, you take a GT module and you look at the largest submodule, which is K locally finite. This functor, I really credit to Harsheimer. I believe it's implicit in this paper on holomorphic discrete series. The difficulty is that Harsheimer was immune to the language of categories and functors. So he talked about this operation as an operation on modules without also discussing operations on morphisms. I really want to think about this as a right adjoint. So, Alexandra, Ron,
Well, the Harsheimer surely introduced Bremen modules.
yes, that's of course another point that I was going to make, yeah. I mean, the naming in this subject is, as usual, quite inaccurate. I'm not going to call this a Harsheimer functor in deference to Harsheimer, who could probably blanch at the name. All right, so this construction was actually around for a long time. It can be used, for example, to give an algebraic description of the principal series of a semi-simple Lie group. And I'll just mention that without going into any details. If you look at Dixie, struggling with it, pronounce his name correctly. Dixie, built me all this. This functor appears quite early in the book and gets repeated over and over again. Perhaps not the relative functor, you might have just considered the case where T is zero. But certainly the idea is in the literature. And the idea which I was somehow led to introduce in the late 1970s was the idea of examining this functor in the language of homological algebra. So at first it's just a functor between the categories. But because I'm working with sufficiently large category, I know that there are sufficiently many injective objects in the domain categories. CGT has, I'll say, resolutions by injective objects. And this is already where category theory is playing a role, because I'm not resolving by injective G modules. The injective G modules are not in this subcategory. They don't have any local finiteness with respect to T. So what I'm talking about is objects in CGT which have the injective property that you learned because of the possibility of conjective resolutions, I can then introduce the derived functors again. This right adjoint functor is also left intact. And so then I can introduce the functors which go from graded GT modules to GK modules. And how are these calculated? You take an injective resolution of a GT module within the category CGT, and then apply the functor gamma. That gives you a new complex, which can now have cohomology. Cohomology of the complex is by definition up-isomorphism R star gamma applied to an object. So let's just write down the formula to have as a comparison. So we're saying that if V is in CGT, as an object, R star gamma KT V is by definition isomorphic to the cohomology of gamma KT I dot, where I dot is my resolution of V. Now this certainly doesn't look very computing. And I'm still asked, what do I need the T for? Why not just do this at the level of, going from G modules to GK modules? And of course, back in the old days, I didn't feel like I had to explain anything. But now, I'm a little bit more generous with these ideas. The point is that let's consider what happens if we apply this functor to the trivial module. So, should I be raising this, or is this? No. Okay. All right. So here's sort of the first result. If you take R star gamma KT and you apply it to the trivial module, then you get the cohomology, K relative T, with trivial coefficients. And then this is something that both algebras and geometers love, because it's the cohomology. And now I will briefly introduce algebraic groups. It's the cohomology of complex algebraic group associated to K divided by the complex algebraic group associated to T. And that's, of course, a very famous topological space. It's a complexification of a compact Taylor manifold, which is one of our favorite manifolds, and we work about it all week. Okay, so that says that there's a great deal of structure for the answer when I include the T in the theory. That's asking answer all questions, but it gives you the first indication that you're dealing with a functor which is certainly not exact and has interesting homological properties. All right, so this is all well and good, but kind of cries out for input. So the input should be a choice of GT for which the derived functors are computable, or at least related to something computable. And now the important thing to understand is that whereas in these very simple examples, you're just getting complex vector spaces, maybe with a ring structure. In general, you're getting a GK module. So this is not a typical cohomology theory from geometry. This is a theory, it's a little bit more like theory of direct images of sheaves under maps, where you're really not passing directly to the cohomology of the sheaf, but you're getting another sheaf on another space. So I want to emphasize that what does it mean to say that I get an interesting answer? It means that I get an interesting one. So the goal, now I guess I should. I realize that I'm putting at least half of me to sleep. I'll let you know when I wake up. So the goal is find these E modules V such that RJ gamma KTE is interesting GK model. Well, in the original application of this theory, I was very interested in the underlying Harshanga modules for the discrete series. So, to greatly oversimplify the history, consider the special case. Okay, symmetric angle rank. And G. And then T equals H at right-hand circle. Of K and G. And then, to try to state this as a theorem would require a fair amount of notation, but the point is that given D lambda and Harshonga's discrete series, call them, M lambda.
What is E lambda?
Sorry?
What is E lambda? I mean, I can't quite read. Harshchandra's,
Chandra's discrete series.
oh, the module.
The module, yes. Yeah, so infinitesimal discrete series. So I'm choosing a weight for H with some appropriate integrality and regularity. And
And of course, he never wrote down representation.
never wrote down the representation, but
He constructed the counter.
okay. As I read discrete series 2, at some point, he actually discusses a Harshchandra module, which eventually becomes that module whose character is already constructed. That module that he writes down lives inside of the Schwarz space. It's not very well described inside the Schwarz space,
All right.
but it's there. It depends upon some arbitrary choices, but it's there. So that's essentially what I'm addressing. Since this is just an example, I'm not trying to write down the theory. What we've seen, the discrete series now is thought of both analytically and algebraically. And by this D lambda, I mean the algebraic module, which is at least implicit in Harshchandra's second paper on the discrete series. So let's say discrete series GK module. So there are natural choices of GT modules. Well, let's make this a singular. Again, to avoid such that D lambda is isomorphic to RS gamma KT M lambda. Where S is half the dimension K mod T. And that is, by the way, an integer under the hypothesis, because T is a part-time subalgebra of K. And Rj gamma KT and lambda is equal to 0 if J is not equal to S. Okay, so the full theorem is certainly stated carefully in many places. I think I stated it correctly in a lecture at Columbia some years ago. So the point is that this is a kind of paradigm for the law. I want to understand, well, can I construct other interesting GK modules? Possibly in the case when K is not symmetric, by making an appropriate choice of GT module. Are there any questions so far? would like to skip ahead to 2014. Because I've already used up a lot of time. So the new theory, coming almost 40 years later, this is around 1977, find categories, or find subcategories of CGT for which R star gamma AT restricted to the subcategory. And I think I wanted to use the word for which. Yields interesting subcategories of CGK. So this is going quite a bit beyond the original example of the discrete series. But I'm still in many ways motivated by what seemed to work back in the 70s. So I have to describe what's a natural way to build some interesting subcategories. Well, I've kind of hinted over here that one should use a Borel subalgebra, which is naturally part of the problem. So let's go back to this. Let's go back to this diagram. Well, if I simply ask that B be a Borel subalgebra of G that interpolates between T and G, it's not a very strong condition. In general, T is not a Cartan subalgebra of G, and there are going to be many Cartan subalgebras of G that contain T and that lie in So I really should draw a more extended picture here. Should really write G and K contains T, and then this picture then H is the Cartan subalgebra of T. T is the Cartan subalgebra of K. As I said before. So there's some flexibility here. If I take an element H in T such that B is equal to the parabolic subalgebra G naturally associated to this semi-simple element T. So let me just say that a little bit more slowly. So since K is acting reductively in G, the T consists of semi-simple elements. For G, and pH is the parabolic subalgebra. Determined by H. And I can think of H as now an element in script H. So that, you can think about it either in terms of roots of H or weights of T. Alright, so there's a well-defined procedure here. And in this case, we're getting a rather strong restriction on G. So what is the consequence of the restriction? So again, let N be now any object in this category associated with this particular age. And I get that RJ gamma KT of N has finite type. Even rather than using that technical term, has finite K multiplicities. Alright, so by construction, the derived function module is a GK module. It's semi-simple over K. But it's not obvious that it has finite multiplicities. And this additional condition guarantees finite multiplicities. Now, there's one slight problem here, and that is that T may be so small that it doesn't contain any regular semi-simple elements. Well, if that's the case, then we look at the piece of H is possibly not of the realm, but we can assume that it's minimal relative to this condition. I think it's easiest for the purposes of this talk just to consider the case where T is regular in G. So otherwise, we're talking about parabolic category O, which is one of the sub-industries of the category O industries. We just probably need another talk on that. All right, so the fact that we get finite K multiplicities is a good sign. Now we should also talk about then, RJ, gamma, AT, N is zero. It's a little bit surprising at first, because first we're doing homological algebra with T. But the answer for the homological dimension only depends on K. Now in the symmetric case, this dimension tends to be rather large if the dimension of G is large. But we're not requiring anymore that K is symmetric. K could be as small as subalgebra isomorphic to SL2. So let's just write down what the result looks like in the SL2 case. Alright, so I realize that several people here worked on the derived function construction in the Horace-Chandra model case, and I'm not mentioning you by name. So maybe I should just say Wilfred and Pavla. Certainly they have made fundamental contributions in the Horace-Chandra model case. Wilfred also succeeded in relating this derived function construction, as it's called for no good reason, to the Bernstein-Davidson classification. But I'm not qualified to state that term. So who have I left out? Alan? Oh, all right, so let's talk about an example from the last 7 years. This has been a long and strange project. That is, assume that K is isomorphic to SL2. That means that, I could be talking about a symmetric case, but there aren't too many symmetric examples, right? SL3, SL3, SL2, and I can talk about SL2, direct from SL2, SL2. So I'm writing down pairs, G and K, and if I understand the classification, these are the only symmetric pairs where the K is isomorphic to SL2. Strictly speaking,
Yeah,
one
the
should
second
go-
case you need a geometry.
Strictly speaking, one should go into geometry. Yes. But our work, where we're assuming that K is isomorphic to SL2 is relevant to this symmetric pair. Okay, so what do we get on the proposition? I'll write it in the opposite order. RJ, M, KT, and this equals to 0 if J is greater than 2. algebra of K, which is now one dimensional. So we can think of it as generated by a single semi-simple element in G. And so in fact, I don't have to make any further assumption on M here. But then in the first case, I have that R, J, M, A, T, N as finite SL2 multiplications for J equal to 0, 1, 2. And that's now under the condition that n is in this much smaller O category. Remember that my category here is a kind of a fictional category where all I'm doing is assuming semi-simplicity with respect to t, but there are no finiteness conditions. Now here I'm assuming that my n is in the O category. And this H is basically the centralized little element H in G. All right, so I started at orbital.
Plus 2 or 3 minutes.
Okay. All right. So let me try to formulate a conjecture. These examples, of course, do not exhaust possible examples. So I could also consider the principle SL2 and G. So the conjecture is for a computable constant n in natural numbers. Let's write let's now write C G B bar T N in the category of GT ones. And the additional conditions that I have in mind here, that technically n plus two. Then I restrict my, my derived functors to the subcategory. That actually doesn't require anything more than that n is possible. But the more crucial thing is that one PT from C, G, E bar T, N to GK modules with finite Hamilton properties. Is an equivalence with its image. Now, we actually have conjecture about the image, but possibly I've used up my time. So thank you very much.
Any questions?
Well, I have a comment maybe. Comment is that, he understands very well the simple objects in that image.
Yes.
And those are precisely the GK modules whose minimal K type has highest weight. Because the minimal K type is now an SL2 representation. So its weight is n or higher. So, but if you compose the GK module over SL2, it just becomes a finite sum of.
Am I allowed to write this down? As
Yeah.
part of the-
This is my comment, that's a comment.
Oh, okay, so that's it's simple and in the image. Then the lowest peak at lowest SL2 type, I want to and conversely, if S is simple and has lowest SL2 type greater than or equal to n, then it's in the image. I'm forgetting one thing here, and that is that one should restrict the weights of T to be integers greater than or equal to n plus 2.
Yeah.
Any other comments or questions? Yes?
Can you say in some examples what is one?
Yeah, what's the bound on n?
Yeah. Okay, so,
The word computable.
yeah. Okay, so we actually estimated in a recent paper. And that maybe gives me the opportunity to plug the alternate station. So by that I mean based on lectures that I gave, looking around for like 2 students from 2009. So I can give lectures here at Jacobs on generalized Harshauer modules. So they now appear on this leakgroups.org site. The most recent paper actually tabulates an estimate for n in the case when G is simple. It's still an interesting problem to extend our methods to semi-simple G. Nowhere in the problem as I formulated it do I need to assume that G is simple, and in fact, this is a great example. Or however, we know that the n has to be 1. So let's see, in the case of examples on the board, which are classical, and I'm cheating a little bit, but in fact, if I take the root as L2, then anything which is of finite type for this pair is automatically a finite type for SL3 comma GL2. So in this case, you make a little table, the n here is 3, and here is 1, and here is 1. And if you look at the classification of modules for this pair, you will see that simplification. And notice that you're throwing out a lot of modules by assuming that the lowest SL3 type has the highest weight at least 3. So it shows that when we go back to the classical theory, there's still a huge gap. We have not offered a new classification for this symmetric pair. Things look a lot better for these 2 symmetric pairs, but still, we have to exclude the case of N equals 0, which looks kind of strange. But of course, for these pairs, the Harshauer models have been known forever. So I think in terms of examples, those 3 symmetric, or nearly symmetric examples already give you some indication. And then the one example which began this whole project back in something like June of 2007. So this is a non-symmetric example. Take G to the as before, 4x4 simplistic matrices, and then you take K to be the principal SL2, and in this case, you have to have n greater than or equal to 5. So in other words, you have to go to the 6-dimensional representation. And here is surprisingly a lot known, and there's also surprisingly a lot known, not understood at all for this particular pair. And it's good exercise for graduate students to figure out which SL2 I'm talking about. I mean, I use some fancy term, but you can write it down in matrices.
Any other question? So, let's say
some theorem for, say, pairs G SL2 or something of this sort. Is there any analog for them for the Harish-Chandra case? So you could say that you could fix some semi-simple element in K and produce kind of similar two categories of just parabolic kind of analogy of a category O with weights which are bigger than some number, and GK models with minimal K type which is bigger than some number.
I would say that Yvonne and I are thinking about that. We need to consider your question. The fact that we're looking at K isomorphic to SL2 is an indication that what we're doing is very primitive. Now I realize I'm making a bad pun because it seems to be a reference to Wilfred's talk on primitive cohomology.
Well, I think,
You have the definition of the SL2 acting on the Taylor calculus?